good idea, that's not resolvable. I can't sort of load this module, oh, but it needs this, so I better load this first, but it needs, I can't do that. So I have to have kind of simple dependencies here. Okay. I don't want to get too kind of in-depth here, because I can kind of go off on a tangent for hours, and then people are going to really hate me. So I'll avoid that. All right, but the point being here, if you go through the slides, I'll put them on the website. It's people.redhat.com/JCM. They're not live right now. I'll just change the file permissions later and they'll be there. But I'm one of these people that like to sort of make sure the slides are there, but not sort of have them available before the talk, because then the talk's still interesting and everyone hasn't already read my slides and knows what's going to be on slide number 23. Okay, so that's how to build a module and how to kind of figure out what it was doing. Right, let's talk more about the kernel architecture. That's fun. Okay, so how do I view the kernel? I view the kernel as a privileged software library. Okay, I like to use that concept. Not everyone agrees with it, but the idea that basically the kernel is not a magical program. Okay, the kernel is not something that runs on your machine all the time. People talk about it like it's this all-seeing thing that's constantly running and constantly doing stuff. That's not true. Okay, the kernel is more like a collection of functions that occasionally do things I want. Okay, and primarily those functions get executed for two reasons. Okay, for two different kinds of reason. They can be asynchronously called or they can be synchronously called. Okay? By asynchronous, I mean things that happen all the time, no matter what else is running. So, on a standard Linux machine, 1,000 times a second, configurably, I have this timer that goes off. Okay, so 1,000 times a second, I get this timer that fires. The hardware at my machine interrupts whatever else is going on and says, tick. Okay, 1,000 times a second. Your machine's sitting there doing this. Tick, 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 tick. 1,000 times every second. Why does it do that? Well, it's convenient for us to schedule certain things to happen from time to time. And it turns out one of the easiest ways to implement that is to have everything be interrupted 1,000 times a second so that we can perform housekeeping functions we might need to do or a whole manner of other things. That's an example of an asynchronous event that just happens. We don't really have any control over it. Hard disk, events, a piece of data becomes available, a network packet comes in. These things kind of tend to happen, whether we do anything, whether we're running a particular program or not, we're still going to get these kinds of events coming in. Okay. We also have synchronous entry into our kernel, and that happens primarily through system calls and things that we ask the kernel to do on our behalf. So if I want to open a file, I want to read some data, I want to write some data, whatever I want to do, if I have to ask my kernel to do it for me, then that's a synchronous entry. So that's two fundamental ways we get in. The kernel's not sitting there kind of in its almighty, some kind of magical context, just sitting there saying, I'm running. It doesn't do that. It's not doing anything most of the time. Most of the time, your programs are running. That's what your machine is there to do. Every once in a while, a piece of code runs that's in the kernel, a privileged piece of code, to perform a specific task. That's what the kernel really is. Nothing more than that. It's not magical. It performs tasks on our behalf. It is privileged. That's the key point. So the kernel can do almost anything, right? Your program cannot. In order for us to maintain this kind of multi-processing concept, this notion that I can run a program here and Bob can run a program there, and they don't interfere with each other, and generally they can't kind of screw each other over, right? That's the whole point here. That's why we have this concept that your program cannot do everything within the machine. It has to ask the kernel to do some things on its behalf. Okay? So it maintains a fundamental software abstraction. It maintains this concept of a process, this concept of a running program. You start the program ls, you start the program bash, you type the command finger, you know, whatever it is that you want to run on your machine. When you run that, that's a program that's running. It's a process on your machine. If you run the top command, the ps command, any of these standard commands, you'll see a list of all the processes running on your machine. You know, on your desktop machine, you'll see, you know, a GNOME terminal process running. It's running your terminal session that you're currently sitting and typing commands into, unless you configured something else as your terminal, in which case you probably know what GNOME terminal is because you got rid of it, and in that case, your other alternative will be there instead. Okay, limits access to shared resources. Kind of old school example is, I want to print something. That guy wants to print something. We can't both print something at the same time. So, you know, we're aware that we have this concept of queuing up print tasks. Well, there are similar concepts at a much lower level for even more basic resources in our machine. Similar kind of mediated control, mediated access, where the kernel's able to decide who gets to access what and when. It's there to help us, not to hinder us, and the goal is for it to be as lightweight as possible. Okay, so the goal here is the kernel's not kind of needlessly doing lots of other stuff. It's basically there to help us to do what we want it to do. That's why we bought the computer. We bought the computer so that we could run our Apache web server. We did not buy the computer probably just to sit there and run the kernel all the time. There's some people who enjoy that, but that's probably not what it was bought to do. So here's another scary diagram. You see, I need to find a better way of doing diagrams. I do these in dia. I export them as transparent PNG files, and you import them into OpenOffice, and it doesn't care if it's transparent. It'll still put a nice white, horrible background there. And I need to find a way to fix that. But this scary diagram shows two processes running on my machine. Okay, so let's say this here is an ls command. Okay, this here is also an ls command. Two different users running the ls command on my machine at the same time. Okay, so what happens? Okay, I've got two different programs, the same program, but two different people are running this program. So they're running the same code. Okay, they're both running the ls command. Okay, so our system is not going to load two copies of the ls program itself. It's going to load one copy of the ls program into memory, and it's going to share that between the two people that are using it at the same time. Okay, they're both running the same code. They're both physically running the same code that's in memory, stored once in memory. Okay, and they're getting different results. Why are they getting different results? Because one of the fundamental things that Linux is doing is managing resources. Okay, the kernel is setting things up so that both these guys can run the same program at the same time, the same code, different data. Okay, and it's maintaining this independence between the two. It's not allowing them to corrupt each other's data. If one of these programs attempts to change some of the data, so my ls command, has some data structures within it. The compiled ls command has some internal data structures that are used while it's running. They get changed. One of these programs tries to change one of those data structures. The kernel is sitting there, and it's automatically keeping, effectively, just the changes my program is making. So it's maintaining all this fancy kind of abstraction, this fancy separation between processes. That's what my kernel's job is to do. Its job is to run processes and to handle resources that those processes require. Okay. So, different kinds of ways we end up in the kernel. Interrupts are one. So I already mentioned the timer interrupt. If you go through the source code on your machine, you can figure out, the different ways in which interrupts can come into your machine. Timer being an obvious one. Here's an example of some of the code for PowerPC machines that covers the timer. Okay, synchronous kernel entry. We already mentioned system calls. What else can happen? various program exceptions could occur. I could try to access some memory that was plainly not my memory. My program's going to segfault, it's going to crash. The kernel's going to have to handle that while the program's running. It's going to have to handle accesses to data in memory. It's going to have to handle, okay, my program just tried to put something onto its stack, but that actually means that its stack is now bigger than the stack I had allocated for it. Okay, so it's going to go ahead and allocate it some more memory. And all these things are happening for us behind the scenes. If you want to look at more within the kernel sources, this is the kind of layout here. What I'm going to concentrate on for the rest of this presentation is the Arch directory and the kernel directory, which is what we're sort of interested in when we're porting Linux to new machines. But some other key directories to look at. We've got documentation. We try to keep an updated set of documentation, documenting changes we make to our kernel. Drivers here contains the drivers that we use in our machine. And a very important file here, reporting bugs. Okay, that is a great file. It tells you how to report a bug when something goes wrong. If you don't know how to fix something, it tells you how to find someone who does. Okay. So then coming on to the main topic, the main sort of reason we're here, kernel portability. Okay. So I had to go through that kind of crash course in kernel building and modules just to make sure we all have some basic notion of these things. But what I really want to talk about is how the kernel is portable from one device to the next. And I'll just stop for a second here and tell you a story. I like stories. This one's about a company I used to work at. As I said, we used to make giant magnets. More specifically, what we used to do was to make imaging systems for MRI, you know, and for measuring samples, for doing all this sort of, not just hospital kind of MRI machines where you can view someone's head, but machines where you can view the inside of a watermelon. Okay, here's another one for you. Did you know that the Japanese love to use MRI machines to look at the inside of watermelons to determine if they're ripe? And if no, it's true. And actually,
that's dedication.
And actually, you can charge $400 for a watermelon you've put into your custom-designed, custom-built MRI machine that can 100% tell you, yes, looking at the graph here, we can clearly see that yes, the water distribution's about right. It's got the right density and consistency, and it's probably right. Okay, $400 a melon if you can accurately determine.
I'd rather buy 200 watermelons and hope one of them is.
But you see, they don't want to do that. They want the guarantee that when I buy that, it's going to be 100% perfect.
For a gourmet high-end restaurant?
This is, I never really spoke to the customer. I'm assuming this is sort of restaurants, I hope. I'm hoping it's restaurants. If it's supermarkets, I'm worried, but I'm hoping it's restaurants.
For my cat.
But the point being that this is a machine that, you know, we've all heard of an MRI machine, we've all heard of going to hospital and having an MRI scan, all this kind of thing. So I looked at this company, we wanted to do something different. We wanted to test out Linux in a new and interesting way. And previously we'd been using DOS and other older operating systems. You know, Windows did factor in there, but not so much. It's not, Windows isn't really geared up for having demanding tasks where we, you know, have deadlines, we want things to happen when we say. Windows likes to take its time and think about doing it, and it might get back to us next Tuesday. So we decided to use Linux, and it was a fascinating learning experience because essentially, you know, this is not the board we used, but for sort of dramatic effect, I'll hold this up. And you know, we took a board like this. We designed the hardware for it. We figured out, okay, what are we going to want? We're going to want to have the processor sounds good. That sounds good. We want the machine to be able to do something. That's great. We want to have some memory. We want to have some flashing lights, because people like those. We want to have some high-speed data.